Welcome to Junior High School Math Series. Many problems in probability theory require that we count the number of ways that a particular event can occur. For this, we study the topics of permutations and combinations. The video lesson on permutation was uploaded prior to this presentation. If you haven't seen it, the link is on the description of this video. In this section, we will study combinations. Combinations is the arrangement of all or part of a set of objects without regard to the order in which objects are selected. In other words, order is not important. Let us again begin our discussion with the letters A, B, and C. Suppose we are asked how many ways we can select two letters from that set without regard to the order of letters. The complete list of possible selection would be AB, BC, and AC. Take note that AB and BA are considered to be one combination because order in which the letter is selected does not matter. This is the key distinction between a permutation and combination. Combination focuses on the selection of objects without regard to the order in which they are selected. Permutation, on the other hand, focuses on the arrangement of objects with regard to the order in which they are arranged. The number of combinations of n objects taken R at a time is given by n combination R is equal to n factorial over n minus r factorial times r factorial. In here, n and r are non-negative integers and r is less than or equal to n. N combination r may be written in different notation. We have n combination r, or we can say n choose r. All of these notations means the same thing, which is the combination of n objects taken R at a time. Let us have some examples. Evaluate 13 combination 5 or 13 choose 5. Here is our suggested solution. From the given information, n is equal to 13 and r is equal to 5. So using the formula, we have 13 choose 5 is equal to 13 factorial over 13 minus 5 factorial times 5 factorial. 13 minus 5 is 8, so we have 8 factorial times 5 factorial in the denominator. From the definition of factorial, we have 13 factorial is equal to 13 times 12 times 11 times 10 times 9 times 8 factorial. We need not expand 8 factorial since we have 8 factorial in the denominator, and a number divided by itself is equal to 1. Also, we have 10 in the numerator, that is equal to 5 times 2 in the denominator, then 10 divided by 10 is equal to 1. Another one, we have 12 in the numerator, and we have 4 times 3 in the denominator, which is 4 times 3 equal to 12. So we have 12 over 12 equal to 1. Then 13 combination 5 is reduced to 13 times 11 times 9, and that is equal to 1287. Example number 2. Solve for n in the following. N choose 3 is equal to 2 times n minus 1 choose 2. Here is our suggested solution. Using the formula, for n choose 3, we have n factorial over n minus 3 since r is equal to 3, n minus 3 factorial times 3 factorial. While in the right hand side, we have 2 times n minus 1 factorial over n minus 1 minus 2 factorial, and that is n minus 3 factorial times 2 factorial. Let us evaluate further. N factorial can be written as n times n minus 1 times n minus 2 times n minus 3. We stop at n minus 3 factorial since we have n minus 3 factorial in the denominator. On the right hand side, n minus 1 factorial is equal to n minus 1 times n minus 1 minus 1, that is n minus 2, times n minus 2 minus 1, that is n minus 3 factorial, and also we stop here because in the denominator we have n minus 3 factorial. 2 factorial is equal to 2 times 1, so we have 2. Then let's do some cancellation since we have numbers or we have factors that are the same in the numerator and in the denominator. First, let us have n minus 3 factorial on the left hand side. Also n minus 3 factorial on the right hand side. Then on the right hand side, we have 2 divided by 2, that is equal to 1. Let us rewrite first so that the equation will be clearer. From this resulting equation, we can divide both sides by the product n minus 1 times n minus 2. So we have n over 6 is equal to 1. Multiplying both sides of this resulting equation by 6, we get the value of n is equal to 6. Let us have example number 3. Given 8 non-collinear points, how many lines are formed by joining any two of these points? Here is our suggested solution. Any 2 points determine a line. From which point the line may be drawn does not matter. Hence, we're going to use the formula for combinations. From the given information, n is equal to 8 and r is equal to 2. So we have 8 combination 2 is equal to 8 factorial over 8 minus 2 factorial times 2 factorial. This is from the formula. So we have 8 factorial is 8 times 7 times 6 factorial. Again, we stop at 6 factorial since 8 minus 2 is 6. So in the denominator, we have 6 factorial times 2 times 1. 2 times 1 is from 2 factorial. 6 factorial over 6 factorial is equal to 1. And 8 times 7 is 56 divided by 2. We have 28. Therefore, 28 lines are formed. Example number 4. 11 medical experts are nominated to form a committee that will identify the new COVID-19 variant found in a nearby province consisting of 6 men and 5 women. 2 women and 3 men are to be selected from this group. How many different possible committees may be formed? Here is our suggested solution. From the given information, 2 women are to be selected from 5, while 3 men are to be selected from 6. Since these 2 are tasks that will be done in 2 consecutive steps, we will use the multiplication principle. So we have 5 choose 2 times 6 choose 3. 5 choose 2 since from 5 women, 2 will be chosen. And 6 choose 3 since from 6 men, 3 will be chosen. 5 combination 2 is 5 factorial over 5 minus 2 factorial times 2 factorial. Multiplied by 6 combination 3, that is 6 factorial over 6 minus 3 factorial times 3 factorial. Evaluating this factorial notation, we have 5 times 4 times 3 factorial. Since 5 minus 2 in the denominator is 3 factorial. And then on the second factor, we have 6 times 5 times 4 times 3 factorial. Also 6 minus 3 factorial is 3 factorial. Then we can cancel some values. 3 factorial over 3 factorial in the first factor is equal to 1. 4 over 2 is equal to 2. Then on the second factor, 3 factorial over 3 factorial is 1. 6 over 3 times 2 is also equal to 1. Then we have 5 times 2 from the first factor times 5 times 4 from the second. So we have 5 times 2 times 5 times 4, and that is equal to 200. Therefore, 200 different committees may be formed. Example number 5. Given 9 points on a circle, how many triangles may be inscribed in the circle if the vertices of the triangle are any of the 9 points? Here is our suggested solution. Since a triangle has 3 vertices, 3 points may be selected from the 9 points on the circle to form an inscribed triangle. Hence, n is equal to 9 and r is equal to 3. So we have 9 choose 3 is equal to 9 factorial over 9 minus 3 factorial times 3 factorial. We expand 9 factorial until 6 factorial because 9 minus 3 factorial in the denominator is 6 factorial. Then 3 factorial is 3 times 2 times 1. 6 factorial over 6 factorial is equal to 1. Also, we have 9 over 3 that is equal to 3. And then we have 8 over 2 that is equal to 4. Hence, we have 3 times 4 times 7 equal to 84. So we have 84 inscribed triangles that may be formed. Example number 6. A committee of at least 4 and at most 6 members is to be formed from a group of 12 delegates. How many different committees are possible? Here is our suggested solution. Forming a committee of 4 members would have no common outcome with forming a committee of 5 members, and so with 6 members. Hence, using the addition principle of counting, we have 12 combination 4 plus 12 combination 5 plus 12 combination 6. These are different committees that may be formed. One with 4 members, because we have at least 4. Another with 5 members, and at most 6, so we have another committee with 6 members possible. So we have 12 factorial over 12 minus 4 factorial times 4 factorial for 12 choose 4. 12 factorial over 12 minus 5 factorial times 5 factorial for 12 choose 5. And 12 factorial over 12 minus 6 factorial times 6 factorial for 12 choose 6. Evaluating these factorial notations, we have 12 down to 8 factorial over 8 factorial times 4 factorial, that is 4 times 3 times 2 times 1, and so with the other addends. 12 choose 5, we end the notation for 12 until 7 factorial because 12 minus 5 in the denominator is also 7. 12 choose 6, we end the notation at 6 factorial because 12 minus 6 in the denominator is 6 factorial. This time, let us do some cancellation. In the first addend, 8 factorial over 8 factorial cancels because that is equal to 1. 12 divided by 4 times 3 is equal to 1. And 10 divided by 2 is equal to 5. In the second addend, we have 7 factorial over 7 factorial, that is 1. 12 over 4 times 3, that is equal to 1. 10 over 5 times 2, that is equal to 1. And then we go to the last addend, 6 factorial over 6 factorial, that is 1. 12 over 4 times 3. Also, we have 10 over 5 times 2, and 9 over 6 is equal to 3 over 2, then 8 over 2 is equal to 4. Next, we have 11 times 5 times 9 plus 11 times 9 times 8 plus 11 times 3 times 4 times 7 left in the notation, and this is equal to 2211. Therefore, 2211 different committees may be formed. Example number 7. How many diagonals can be drawn in a dodecagon? Here is our suggested solution. A dodecagon has 12 vertices. Relating to example number 3, the number of line segments that can be drawn from these 12 vertices that are non-collinear is given by 12 combination 2. And all these segments may be counted as diagonals except for the 12 segments which are the sides of the dodecagon. Now let D be the number of the diagonals. Then we have D is equal to 12 combination 2 minus 12. Then we have 12 factorial over 12 minus 2 factorial over 2 factorial minus 12. 12 factorial is 12 times 11 times 10 factorial, since we have 12 minus 2 factorial in the denominator. So 10 factorial over 10 factorial is equal to 1. And 12 over 2 is equal to 6. So we have 6 times 11 minus 12. And that is 44. Therefore, 44 diagonals can be drawn in a dodecagon. That will be all. Thank you for watching. Please subscribe for more math lessons.